A star's journey is plotted on a map that is constantly stretching. This is the long-term journey of stars moving through expanding space, and it is not a simple path through a fixed universe. You will gain a completely new understanding of how the cosmos works, from the forces guiding a star's birth to its final resting place in a dark, isolated future. We will uncover how dark energy is steadily pulling the universe apart, and ask what happens when all other galaxies vanish from sight. How does it change your sense of place to know that even the stars are travelers on an endless, expanding road? This stretching of space is a subtle but relentless force. Think of the universe as a loaf of raisin bread dough rising in an oven. The dough itself represents the fabric of space. As it expands, every raisin, which is like a galaxy or a cluster of stars, moves away from every other raisin. It is not that the raisins are traveling through the dough on their own. Instead, the dough between them is stretching, carrying them apart. This is the fundamental reality for every star. Its motion has two components. First, there is its local journey, perhaps orbiting the center of its own galaxy, drawn by the immense gravity of a supermassive black hole and all the other stars around it. This is the path we are most familiar with. But second, and more profound for its ultimate fate, is that the entire galaxy it calls home is being carried along by the expansion of space itself. The stage is not just changing, it is growing, and every actor upon it is being steadily, inexorably repositioned. This dual motion, the local dance and the cosmic drift, defines the long-term voyage of every star in the sky. So when you look up at a distant galaxy, you are not just seeing an object far away. You are witnessing a traveler on a current of expanding space, beginning a journey into a future of increasing isolation. What does that mean for the light it emits, for the very signals it sends across the void? That rising loaf of bread gives us a powerful image, but the real discovery was far more precise. Astronomer Edwin Hubble noticed something extraordinary. The light from distant galaxies was not just faint. It was shifted toward the red end of the spectrum. This redshift was a cosmic signature, revealing that these galaxies were all rushing away from us. More than that, he found a direct relationship. The farther away a galaxy is, the faster it appears to be receding. This is the Hubble Flow, the smooth, relentless outward drift of the cosmos on its very largest scales. For a star nestled inside its home galaxy, this is the primary current it rides. It is less like a fish swimming in a river and more like a passenger on a vast, cosmic vessel, carried along by the expansion of space itself. The star's own local motions, its orbit around the galactic center, are tiny in comparison to this grand, universal pull. This flow dominates the emptiness between galaxy clusters, creating the overarching structure of our expanding universe. Yet this raises a profound question. If everything is flowing apart, what force could possibly hold anything together? Our own sun provides a perfect example of this cosmic tug-of-war. It is not sitting still. It is whipping around the center of our Milky Way galaxy at incredible speed, completing one full orbit roughly every 230 million years. This is the power of local gravity, a force strong enough to bind billions of stars into a single, spinning disk. Yet simultaneously, our entire galaxy, the Sun and all its stellar siblings included, is caught in the Hubble Flow, the relentless expansion of space on the grandest scale. Think of it as two different kinds of motion happening at once. The star has its own local velocity, its orbit around the galactic center. Then, layered on top of that, is the recessional velocity given to it by the stretching of space itself. The actual path a star takes is the combination of these two forces. It is not a simple circle, nor is it a straight line flying away. Instead, its journey resembles a corkscrew, a spiraling path through a medium that is itself continuously stretching. As astrophysicist Priyamvada Natarajan describes it, gravity creates stable islands of matter, like galaxies and galaxy clusters, within the overall expanding ocean of the cosmos. These islands are where local bonds triumph, at least for now, over the cosmic drift. This complex interplay between the intimate pull of gravity and the vast push of expansion defines every star's unique trajectory. It makes you wonder, what were the initial conditions, the precise starting point and velocity, that set our Sun on its particular corkscrew path through the universe? This question of origins brings us back to the very beginning of a star's life. Every star begins its life with a unique cosmic inheritance, deep within a glowing stellar nursery like the famous Orion Nebula. A dense knot of gas and dust collapses under its own weight. The precise location of this event, the spin of the cloud, and the gravitational tug from all the surrounding material, these are the initial conditions that will define its voyage for billions of years. A star ignited in the crowded, violent core of a galaxy is born into a gravitational maelstrom. Its path will be a tight, frantic orbit, constantly jostled by the immense pull of the central supermassive black hole and the dense swarm of neighboring stars. In contrast, a star forming in the quiet, sparse outskirts of the galactic halo experiences a far gentler gravitational field. Its journey will be a long, slow, looping arc, a solitary trek through the galactic frontier. This natal environment is the first and most crucial factor, setting its initial speed and direction. But the launch is not always smooth. The violent explosion of a nearby supernova can give the newborn star a powerful kick, altering its course before it even settles into maturity. Or gravitational interactions with its stellar siblings can sling it onto a new path, like a pebble tossed from a spinning wheel. These initial parameters, this specific combination of place and momentum, become the star's personal sail, the first push that sends it on its way. From this moment, the star is a traveler, its epic saga written in the fundamental laws of physics. Its entire future, the complex corkscrew path it will trace through the expanding universe, is an unfolding consequence of this single, fiery point of origin. So we must ask, with such a turbulent beginning, how does a star ever find a stable path to follow? This silent cartographer of the cosmos, dark matter, maps the paths of stars with an invisible hand. While we see the glittering spiral arms of a galaxy, this luminous structure is merely the inner core, a small part of a much larger and more massive entity. The galaxy is enveloped in a vast, spherical halo of dark matter, a form of matter that does not interact with light, but whose gravitational influence is profound. It is this unseen halo that dictates the orbital dance of every star within its grasp. The mystery of its rotation curve provides the clearest evidence. Based on the visible stars and gas alone, we would expect stars at the outer edges of a galaxy to orbit much more slowly than those near the bright center, just as Pluto moves more sluggishly around the Sun than Earth does. Yet observations reveal a startling truth. Stars in the distant galactic hinterlands whip around at nearly the same high speed as those closer in. Something unseen must be providing the extra gravitational glue to hold these fast-moving outliers in their paths. That something is the dark matter halo, its gravitational field creating a deeper and more extensive well of attraction than visible matter can account for on its own. A star's long-term journey, therefore, is not just a response to the glittering city at the galactic center, but to the entire invisible country that surrounds it. Its orbital speed, its orbital period, the very shape of its corkscrew path through expanding space are all fine-tuned by this dark architect. This raises a humbling thought. The star you see twinkling in the night sky is tracing a course set by a substance we cannot see, a reminder that the universe is governed more by the darkness than by the light. What happens then when the universe itself begins to pull this intricate guidance system apart? But this cosmic cartography, this grand map drawn by dark matter, is not fixed for all time. A deeper and more mysterious force is at work on the canvas of space itself, one that rewrites the rules of the journey. This is the relentless push of dark energy. While dark matter sculpts the islands of galaxies with its gravitational pull, dark energy is the pressure in the empty ocean between them, a form of anti-gravity that permeates the very vacuum of space. Its discovery was one of the most shocking in modern cosmology. Teams led by scientists like Saul Perlmutter were observing distant supernovae, expecting to measure how much the universe's expansion was slowing down due to the collective gravity of all matter. Instead, they found the opposite. The universe's expansion is not slowing, it is speeding up. This acceleration earned them the Nobel Prize and unveiled a cosmos dominated by a repulsive force we are only beginning to comprehend. For our traveling star, dark energy's influence is imperceptible on human timescales, a whisper against the roar of galactic gravity. Yet over billions of years, this whisper becomes a constant, mounting pressure. It does not tear apart individual stars or solar systems, as local gravity holds firm. Its power is exerted on the vast, empty tracts between galaxy clusters. Dark energy works against gravity's pull on the grandest scales, steadily making it harder for cosmic structures to hold onto one another. It is this accelerating push that will ultimately dictate the final, lonely chapters of a star's journey, steering the entire cosmos toward a future of profound isolation. If dark matter is the architect of galactic paths, then dark energy is the force that will one day dissolve the map itself. What does this accelerating universe mean for the ultimate destination of every star we see? This cosmic tug-of-war between gravity and expansion is a battle fought over eons. In the universe's youth, gravity held unquestioned sway. Its patient pull gathered sparse clouds of primordial gas, drawing them into the first stars and then into the brilliant, swirling assemblies we call galaxies. For billions of years, gravity was the great architect, building the cosmic structures that define the night sky. But the balance of power is not static. As the universe grows larger and more diffuse, the nature of the vacuum itself changes. Dark energy, a property of empty space, gains the upper hand. Its repulsive push does not destroy galaxies from within, but it works to isolate them from without. The space between galaxy clusters, already vast, is stretched even further, turning a scattered archipelago of islands into isolated kingdoms separated by an ever-widening sea of nothingness. For a single star, this grand conflict is felt as a matter of allegiance. Its local gravity, the bond to its galactic home, remains unbroken. The star continues its orbit, held fast by the immense collective mass of its neighbors and the encompassing dark matter halo. Yet the entire galaxy it belongs to is now adrift, carried by the Hubble Flow on a course of increasing separation from all other galactic families. The star's experience is one of dual reality. It is both securely bound to its celestial city and a passenger on a vessel that is sailing forever away from all other ports. This dynamic equilibrium defines its journey. The local bonds triumph for now, but the cosmic currents are shifting, steering the entire system toward a future of profound solitude. What happens when this isolation becomes complete? When the last lights of other galaxies fade from view forever? Trillions of years from now, the cosmic horizon will have closed in completely. The grand archipelago of galaxy clusters, once scattered across the observable universe, will have vanished over the edge of sight, dragged away by the accelerating expansion of space. All that remains is a single colossal island in the void. Our Milky Way and its great neighbor, the Andromeda Galaxy, will have long since completed their slow, gravitational dance, merging into a final, solitary structure astronomers call Milkdromeda. For a star born in this far future epoch, the universe is a profoundly different place. Its journey is no longer a trek between great clusters on the cosmic current. The star's entire existence, its entire long-term path, is now confined to the borders of this one immense galaxy. The expansive phase of its voyage is over, replaced by an eternal, looping orbit within this last bastion of light. This is the ultimate fate of galactic clusters, to become isolated island universes adrift in an ever-darkening sea. Think of it as a ship that once sailed a vast ocean, only to find the ocean has evaporated, leaving it forever beached on the only land in existence. The star's motion is now dictated solely by the final, stable gravity of Milkdromda. It will trace elegant, predictable ellipses around the galactic core, a permanent resident of the only city left in the cosmos. This raises a poignant question about the star's own life cycle within this solitary home. How does a star live and die when it is part of the last generation, when the universe outside its galaxy is an impenetrable curtain of blackness? The life story of a star is written not just in its own heart, but in the grand theater of the expanding cosmos. A star like our Sun appears to follow a predictable script, its lifespan and final fate sealed by its initial mass and chemical makeup. Yet the relentless stretch of space introduces quiet, background notes that subtly rewrite this narrative over eons. One of the most profound changes is the cooling of the cosmic microwave background, the faint afterglow of the universe's birth. This radiation bathes all of space, and as the universe expands, this bath grows colder. For now, its influence is negligible, but over trillions of years, this cooling will become a defining feature of the cosmic environment. Simultaneously, the density of the raw material for new stars, the thin gas drifting between galaxies, is being ever more diluted. The expanding universe is, in effect, slowly turning down the heat and clearing out the workshop where future stars are built. This means that the very conditions for star formation in the far, far future will be fundamentally different from those in our own vibrant cosmic era. The universe is making it harder for new stars to be born, but a star's own journey within its galaxy also shapes its legacy. A star forged in the crowded, metal-rich core of a galaxy is born from the ashes of countless previous stellar generations. Its composition is complex, heavy with elements that are the building blocks for rocky planets and, potentially, life. This star's life and death will enrich its immediate surroundings, seeding the next cycle of star birth in a bustling galactic center. In stark contrast, a star born in the pristine, sparse outer halo forms from gas that has remained relatively untouched. Its composition is primitive, dominated by the primordial hydrogen and helium from the dawn of time. The planets that might form around such a star would be gaseous worlds, lacking the heavy elements necessary for rocky surfaces. Its journey through these different galactic environments, a path set by the initial conditions of its birth and the invisible hand of dark matter, directly influences the resources available for planet formation and for fueling future stellar generations. The expansion of space, therefore, is the ultimate stage director. It controls the long-term availability of cosmic resources and guides the star's motion through the varied neighborhoods of its galaxy. This connects the immense, macro-scale fate of the entire universe to the intimate, micro-scale story of a single star's existence, from its fiery birth to its final contribution to the galactic ecosystem. How, then, does this grand narrative conclude for the star itself, when its own internal fires finally begin to fail? That twinkling point of light is not a fixed beacon. Its subtle drift across the celestial sphere, a shift so slight it is measured in milliarcseconds per year, is its proper motion. This is the star's local gate, the reflection of its personal orbit around the galactic center. It is the motion we can chart directly, a slow crawl against the backdrop of more distant stars. Yet when we analyze its light with a spectroscope, we uncover a second, more profound story. The star's spectral lines are stretched, shifted toward the red. This redshift is not a measure of its local dance, but of its participation in the grand Hubble Flow. It tells us the recessional velocity, the speed at which the expanding fabric of space itself is carrying the star's entire galaxy away from us. To understand the star's true path through the cosmos, we must disentangle these two signals. The proper motion reveals its lateral shuffle within its galactic home, while the recessional velocity reveals the speed of the cosmic river carrying that home away. An astrophysicist observing this star is like a scientist tracking a bird flying inside a moving train. They must measure the bird's flapping wings and its direction within the carriage, the proper motion, while also accounting for the train's own relentless speed down the tracks, the recessional velocity. Only by combining these two datasets, the tiny angular shift and the spectroscopic redshift, can they compute the star's true velocity vector. This precise astrometry reveals the intricate reality of its journey, a spiraling path that is neither a simple orbit nor a straight-line flight, but a complex combination of both. It is the sophisticated tool that allows us to peer beyond the illusion of a static sky and witness the dual reality of every star's existence. So if we can map this complex motion for stars today, what does it reveal about the ultimate fate of their journey as dark energy continues to accelerate the expansion of space itself? The Gaia spacecraft is building a living atlas of our galaxy's motion. This ambitious observatory is not merely taking pictures of the stars, it is measuring their positions with astonishing precision, charting the subtle drift of over 1 billion suns. This vast census provides the raw data for tracing stellar paths across cosmic time. To understand a star's complete journey, astronomers must know 3 fundamental things: its distance, its motion sideways across our line of sight, and its motion toward or away from us. Gaia excels at the first 2, employing a technique called parallax. Think of holding your thumb out and closing one eye, then the other. Your thumb appears to shift against the background. Gaia does this on a galactic scale, observing a star's apparent shift from opposite sides of Earth's orbit around the Sun. This tiny angular shift, measured with exquisite accuracy, reveals the star's distance. Simultaneously, Gaia tracks the star's proper motion, its slow crawl across the celestial sphere. But this is only 2 dimensions of a 3-dimensional story. To complete the map, we need to know if the star is moving toward us or away from us. This is where spectroscopy comes in. By analyzing starlight with powerful telescopes like Hubble and the James Webb Space Telescope, astronomers detect the Doppler shift. If a star is moving away, its light waves are stretched, shifting toward the red end of the spectrum. If it is moving closer, the waves are compressed, shifting toward blue. This redshift or blue shift gives us the star's radial velocity, the 3rd critical piece of the puzzle. By weaving together Gaia's positional data with spectroscopic velocity measurements, scientists can construct a full 3-dimensional velocity vector for each star. It is a cosmic cartography project of unparalleled scope, transforming a static star chart into a dynamic movie of our galaxy's evolution. We are no longer just looking at a snapshot, we are learning to watch the film of our galaxy's life, frame by painstaking frame. This powerful synthesis of data allows us to rewind the celestial clock, reconstructing where stars have been and to fast forward, projecting their future trajectories through the expanding void. It is through this intricate detective work that we can truly witness the long-term journey of stars, not in a single human lifetime, but through the accumulated legacy of observation and the brilliant light of inference. What profound secrets about our galaxy's past and future might be hidden within this vast and flowing stellar river? Our own sun offers a perfect lens to watch this cosmic choreography in action. We know its current address, a suburban location about 26,000 light-years from the bustling core of the Milky Way. Here, It completes a stately circuit around the galactic center once every 230 million years, a journey it has repeated nearly 20 times since the age of the dinosaurs. But this familiar path is not its permanent route. In approximately 4 to 5 billion years, our galaxy will begin its long-anticipated merger with the Andromeda Galaxy, a slow-motion gravitational embrace that will utterly reshape the stellar neighborhood. During this colossal rearrangement, the Sun will not be a mere spectator. The immense gravitational forces at play will act like a cosmic slingshot, likely perturbing its orbit and flinging it outward onto a new, wider trajectory within the newly formed Andromeda Galaxy. Its local path will be fundamentally altered, a direct result of galactic evolution. Yet through this entire local upheaval, a grander motion continues unabated. The entire local group of galaxies, including Andromeda itself, is a passenger on the Hubble Flow, steadily receding from all other galaxy clusters in the observable universe. The Sun's ultimate journey is this profound duality, a changing local orbit within a consolidating galaxy, all while riding the relentless wave of cosmic expansion. It is a single, shining microcosm of the universal stellar experience, a reminder that even our own star is a traveler on an endless road. To make sense of this grand cosmic drift, scientists use a brilliant conceptual tool, a natural grid for the expanding universe. This is the framework of Comoving coordinates. Imagine the entire fabric of space as a vast, flexible sheet of graph paper, where every single line is stretching uniformly as the universe grows. An object that is simply riding the Hubble flow, carried along by the expansion of space itself, stays fixed on this grid. Its comoving distance to us remains constant, because the grid itself is its frame of reference. It is, in a cosmic sense, at rest. This is the first and most fundamental component of any star's journey, the passive drift on the river of space. But stars are not merely passive. They have their own local motion, their orbits within galaxies, their gravitational dances. This individual effort is termed the peculiar velocity. This is the star's own swimming against, or with, the cosmic current. It is this peculiar velocity that creates the complex, corkscrew path we discussed, the local dance superimposed on the grand drift. By separating the universal expansion from these local movements, the Comoving coordinate system untangles an incredibly complex problem. It allows a cosmologist to write manageable equations, to model a star's voyage as a simple sum, its fixed position on the stretching grid plus its own unique swimming motion. This distinction is not just academic. It is crucial for accurately projecting the future position of any object in the cosmos, from a nearby star to a distant quasar. It is the mathematical key that lets us rewind the expansion of the universe to understand the Big Bang, and to fast forward to predict the ultimate fate of galactic clusters. This elegant separation of motions reveals a profound truth, that the universe's expansion is the background upon which all local stories are written. So if we can pinpoint a star's place on this universal grid and measure its personal swim, what grand cosmic forecast can we then make for its final, isolated destination? The serene cosmic drift of a star is sometimes violently interrupted. Across billions of years, the slow dance of galaxies can turn into a headlong rush, a gravitational embrace that shatters all prior trajectories. The impending merger between our Milky Way and the Andromeda Galaxy is a perfect example of this cosmic upheaval. As these two colossal islands of stars draw together, their mutual gravity begins to warp their majestic spiral arms into long, streaming tails of starlight. It is a chaotic yet beautiful rearrangement, a billion-year-long ballet of destruction and creation. Within this maelstrom, the journey of an individual star is thrown into chaos. The predictable corkscrew path it has followed for eons is suddenly erased. The star finds itself in a gravitational free-for-all, where the rules of motion are rewritten in an instant. The vast distances between stars mean direct collisions are extraordinarily rare, but their courses are bent and twisted by the shifting gravitational landscape. Some stars receive a gravitational slingshot, a kick so powerful it ejects them entirely from the new galactic system. They become rogue stars, cast out into the black emptiness of intergalactic space, destined to wander the void alone, their light fading into permanent isolation. Others experience the opposite fate, their new path sending them diving inward on a wild, plunging orbit toward the frenetic core of the merging galaxies. There, they may swing perilously close to the newly combined supermassive black hole, or find themselves jostled into a dense, crowded stellar environment unlike anything they have ever known. This galactic merger is a dramatic punctuation mark in the star's long-term story. For billions of years, its journey was defined by the steady pull of dark matter and the slow drift of expansion. Then, in a relatively brief cosmic moment, its path is violently rerouted by a local cataclysm. It is a powerful reminder that a star's voyage is not always a smooth, predictable curve through expanding space. It can be a story of sudden, wrenching change, where the local forces of gravity can, for a time, completely override the grand, background narrative of the cosmos. What becomes of these stellar travelers, the ones cast out into the eternal night between galaxies? A star flung from its galaxy becomes a true cosmic exile. These are the hypervelocity stars, first envisioned by astronomer Jack Hills, and their creation is one of the most violent events a star can endure. The most common catalyst is a close gravitational dance with a supermassive black hole at the galactic center. In a binary star system drifting too near this cosmic monster, one star may be captured into a tight orbit, while its companion is slingshotted outward with such immense force that it achieves escape velocity. In a single, catastrophic moment, it breaks free from the gravitational bonds of its entire galaxy, becoming a rogue star set adrift. Its new journey is one of profound solitude, a lone voyage through the immense, dark voids between the great filaments of the cosmic web. Once ejected, the star's motion simplifies in a haunting way. Stripped of the complex gravitational pulls from its galactic home, its path is no longer a corkscrew or an ellipse. Its own peculiar velocity, the speed of its initial ejection, points it in a single direction like an arrow. From that moment on, its journey is almost purely governed by the Hubble Flow. It becomes a perfect passenger on the river of expanding space, its trajectory smoothing into a straight line when plotted on the universe's Comoving coordinates. This is cosmic expansion in its purest form, experienced by a solitary traveler with no local ties to distort the signal. These stellar exiles offer a unique window into the forces shaping the cosmos. By studying their speeds and trajectories, astronomers can trace them back to their galactic point of origin, like finding the source of a single, high-speed projectile. This forensic astronomy reveals the dynamics of the violent environments that spawned them, particularly the regions surrounding supermassive black holes. Their solitary light, traveling through the near-perfect vacuum of intergalactic space, is unaffected by the gas and dust that complicates observations within galaxies. They become pristine probes of the intergalactic medium and the overarching influence of dark energy. Yet their fate is one of ultimate isolation. While stars bound within galaxies will continue their dances for trillions of years inside merged supergalaxies like Andromeda, a hypervelocity star is on a one-way trip into nothingness. It will never encounter another star, never feel the gentle tug of a new galactic home. As the universe expands, the space around it stretches ever further, ensuring its solitude is permanent. Its light will slowly dim as its nuclear fuel is exhausted, and it will end its days not in a crowded galactic center, but in the immense, silent blackness between the islands of light. It is the ultimate manifestation of a journey defined solely by the expanding void, a single point of light on an endless, straight road to nowhere. What does the existence of such permanent exiles tell us about the final distribution of matter in a dark energy-dominated universe? Trillions of years from now, the stellar population has undergone a profound transformation. The vibrant, star-forming galaxies of our era are gone, replaced by a cosmos entering the degenerate era. The last blue and yellow suns, like our own, have long since burned out, their nuclear fuel exhausted. The grand cycle of star birth and death has ground to a halt, as the raw materials for new stars have been stretched into invisibility by the relentless expansion of space. What remains is a galaxy populated by the most frugal and enduring of stellar objects. Faint, cool red dwarfs, some with lifespans longer than the current age of the universe, continue their slow burn. They are outnumbered by the stellar remnants, the final products of stellar evolution, white dwarfs, neutron stars, and black holes. These are the cooling embers of a once brilliant cosmic fire. For these last stars, the concept of a journey has fundamentally changed. The dynamic, dual-layered voyage through an expanding universe is over. The external galaxies vanished from view eons ago, their light stretched beyond detectability by the accelerating cosmos. The grand stage has shrunk to a single, isolated galaxy, a lone island in an infinite, ever-darkening sea. Within this last bastion, the journey of a star is now a simple, solemn procession. Its motion is reduced to a slow, gradual orbit around the galactic center, a silent, looping path with no external reference points. There are no new star clusters to approach, no galactic neighbors to gravitationally influence its course. The complex corkscrew path has smoothed into a near-perfect, predictable ellipse, a final, eternal dance in the dark. The universe, once a tapestry of flowing light and motion, becomes a much quieter place, where the very idea of a cosmic journey carries a new, more solitary meaning. The vast cosmic web is the ultimate architecture of our universe. This intricate structure, composed of immense filaments of dark matter and galaxies surrounding enormous, nearly empty voids, is the final and largest scale that guides a star's journey. Where a star is born within this web, whether in a dense knot of galaxies or a desolate intergalactic desert, imprints a fundamental bias on its motion. A star forming within a massive supercluster, like our own Laniakea, is born into a gravitational metropolis. Its path is not only defined by the pull of its home galaxy, but by the combined, subtle tug of the entire filamentary structure it resides within. This adds a gentle but persistent directional drift to its motion, a slow current within the larger cosmic river, guiding its galaxy along the invisible roads of the dark matter web. In stark contrast, consider a rogue star already cast adrift into one of the universe's great voids. Here, the density of matter is so low that local gravitational pulls are almost non-existent. For this stellar exile, the Hubble Flow is the dominant, almost pure, force. Its motion is a near-perfect straight line on the Comoving grid, a solitary traveler moving with the smooth, unperturbed expansion of space itself. This is the influence of large-scale structure, a final layer of complexity that ensures no two stellar journeys are ever truly identical. A star's long-term trajectory carries the signature of its address in the cosmic web, a permanent record of whether it began its life in a crowded urban cluster or the most remote countryside of the cosmos. Beyond the steady pull of gravity and the grand drift of expansion, there exists a more subtle, almost ghostly influence on a star's path. The fabric of spacetime itself is not a perfectly still pond, but a dynamic medium that can ripple and wave. These are gravitational waves, generated by the most violent events the universe can muster. When two immense, dense objects like black holes or neutron stars spiral into a final, cataclysmic merger, they shake the very foundations of reality, sending out waves of distortion that travel at the speed of light. As these ripples pass through a star system, they do something extraordinary. They minutely stretch space in one direction and compress it in another, a distortion so tiny it is nearly impossible to comprehend. For a single star, the effect of one such wave passing by is vanishingly small, a shift in position smaller than an atomic nucleus. It is a whisper against the roar of its orbital motion. Yet over the course of billions of years, a star is bathed in a cosmic sea of these whispers. It is subjected to a continuous, random background of spacetime ripples from countless mergers happening across the universe. Each event imparts an almost negligible push or pull, a stochastic kick to the star's velocity, while the deterministic forces of gravity and dark energy set the broad, predictable arc of its journey. This cumulative effect from gravitational waves adds a layer of fundamental randomness. It is a phantom force, a subtle perturbation that means no two stellar journeys, even with identical starting conditions, would ever be exactly the same. This reminds us that the cosmos is not a clockwork mechanism, but a vibrant, vibrating entity where even the vacuum hums with the echoes of distant violence. How do we possibly detect such a faint, universal whisper amidst the cosmic noise? This growing isolation is not merely a future abstraction. It is a mathematical certainty written into the fabric of space-time. As the universe's expansion accelerates, a threshold is crossed. The space between distant galaxy clusters begins to stretch at a rate that exceeds the speed of light. This does not violate the cosmic speed limit for objects moving through space, for it is space itself that is stretching, carrying the galaxies apart faster than a photon can bridge the growing gap. When this happens, a galaxy effectively crosses a cosmic event horizon. Its final photon is emitted, a last message that will eventually struggle across the void and reach us, but every bit of light it sends after that is trapped. The expansion of the intervening space outruns the light's own flight, dooming it to travel forever in a growing distance it can never overcome. That distant galaxy has not vanished in a flash, it simply fades from all future possibility of contact, like a ship sailing over the curvature of the Earth. Its mast the last thing to disappear from view. For a star within our own Milky Way, this is a slow, relentless closing of the curtains. The external universe it can know, the universe it can interact with through light or even the faint whisper of gravity waves, is perpetually shrinking. Its journey continues, a spiraling path through its galactic home, but the stage lights are going out, one by one, across the cosmic auditorium. The star becomes a traveler on a ship whose portholes are steadily blackening, sailing into a future where the only reality is the vessel itself. All other points of reference, all other sources of light and information, will have receded beyond an unbreachable horizon. This is the journey into informational oblivion, where the cosmos forgets itself, and every star's story becomes a solitary one told in the dark. Every star's path is a story that began before the first star even existed. The grand narrative of cosmic motion traces back to the universe's very first moments, to a seed of structure planted in an unimaginably hot, dense state. In that initial singularity, the cosmos was not perfectly smooth. It was imprinted with minuscule quantum fluctuations, random variations in density that were smaller than a single atom. Then, in a fleeting instant of inflationary expansion, the universe underwent a growth spurt of epic proportions, stretching these tiny ripples to macroscopic scales. Those amplified wrinkles in the fabric of reality became the primordial inhomogeneities, the slight overdensities and underdensities that would dictate the entire future architecture of the cosmos. Where the density was just a fraction higher, gravity had a slight advantage. Over billions of years, that tiny head start allowed matter to accumulate, pulling in more and more gas from the surroundings. These gentle hills became towering mountains, the great gravitational wells that would eventually cradle entire galaxies and the clusters they call home. The specific location where a star ignites is not random. It is the direct descendant of one of these ancient density peaks. The gravitational potential of that local region, sculpted by the initial conditions of the universe, sets the stage for the star's entire journey. Its orbital speed, the shape of its path, and even the ultimate fate of its galactic home are all consequences of the gravitational cascade that began over 13.8 billion years ago. This means the corkscrew path of a star like our Sun, a path we can measure with spacecraft like Gaia, is not merely a product of recent galactic history. It is the final expression of a pattern written at the dawn of time, a single thread in a tapestry whose weaving started in the first fraction of a second of everything. The universe remembers its beginnings, and every star is a living reminder of that first, faint whisper of structure. To chart a star's voyage across billions of years, we must build our own universe inside a machine. Supercomputers take on this monumental task, running intricate codes that model the fate of billions of virtual particles under the relentless pull of gravity and the steady push of cosmic expansion. In projects like the Millennium Simulation, these digital particles act as stand-ins for entire galaxies or clusters of stars, tracing out the evolution of cosmic structure from the early universe to the distant future. This is not a simple animation. It is a rigorous calculation of physics on a scale almost beyond comprehension. Researchers can input different rules for the invisible actors, dark matter and dark energy, and then fast-forward the clock. They watch as their simulated stars begin their long-term journeys, their paths weaving through the growing cosmic web, their velocities a complex sum of local orbits and the grand Hubble Flow. Does a particular model of dark matter lead to galaxies that are too spread out? Does a specific strength of dark energy cause galaxy clusters to fly apart too quickly? These digital laboratories provide the answers, allowing us to test our most fundamental theories about the cosmos against a synthetic reality. It is through these simulations that we can witness the ultimate fate of stellar populations, watching as the vibrant archipelago of galaxies slowly dissolves into isolated islands, all within the span of a few days of processing time. They offer a powerful glimpse into processes that unfold over timescales that dwarf human history, a synthetic window into the final, lonely chapters of every star's epic journey. This ability to map a star's journey raises a profound question about our own place in the cosmos. We exist in a remarkably balanced era for observation, a narrow window in the universe's long history where such studies are even possible. Billions of years ago, the cosmos was an opaque, swirling fog of primordial gas, with no stars to chart. Trillions of years from now, the accelerating expansion will have carried all other galaxies beyond the visible horizon, leaving our night sky almost entirely black. We happen to live in the sweet spot in between, a golden age of cosmology where the universe is both transparent and richly structured. This is not necessarily a mere coincidence. The anthropic principle offers a philosophical lens for this reality. It suggests that the universe we can observe must, by necessity, be compatible with the existence of observers like ourselves. The very fact that we are here to measure the redshift of galaxies and track stellar motions implies we live in a place and time where such phenomena are accessible. Our cosmic address is not random, it is self-selecting. We could not find ourselves in a future era of permanent isolation, because there would be no one to ponder the isolation. We could not have existed in the first fiery moments after the Big Bang, as the building blocks for life had not yet been forged in stellar furnaces. Our presence here now is intertwined with the observable conditions we take for granted. The long-term journey of stars is not just a subject we study from a detached, external viewpoint. Our capacity to understand it is a fleeting, precious feature of this specific cosmic epoch, a transient moment of cosmic self-awareness before the final lights go out. What does it mean for our search for meaning? To know that our window for understanding the universe is both miraculously open and inevitably closing. This conservation of energy presents one of the most subtle puzzles in all of cosmology. In the closed system of a laboratory, energy is neither created nor destroyed. It simply changes form. Yet our universe is not a closed, static box. It is a dynamic, stretching fabric. And this expansion forces us to rethink what energy even means on the grandest stage. Consider the journey of a single photon from a distant star. As this particle of light travels for billions of years through the expanding void, its wavelength is relentlessly stretched by the growing space it traverses. This cosmological redshift saps its energy, making it appear cooler and redder by the time it finally reaches our telescopes. So where did that energy go? It was not destroyed. In the framework of general relativity, that lost energy is essentially transferred to the gravitational field of the universe itself. The work done by the expanding cosmos on the photon results in a net energy gain for the gravitational field, a cosmic ledger that remains balanced in a way that is profoundly different from the simple conservation we learn in school. The same expansive force reshapes a star's own kinetic energy. A star's peculiar velocity, its own swim through space, can be thought of as a localized store of motion. But as the universe expands, this motion is subtly diluted. It is like a swimmer fighting a current that is gradually strengthening. The swimmer expends energy to maintain their position relative to the riverbank, and their personal store of energy is slowly depleted by the relentless flow. For a star, this means its peculiar motion, relative to the comoving grid of the cosmos, can very slowly decrease over eons as the expanding space acts against it. This does not violate any physical laws. It simply reveals that in an expanding universe, the very definition of a conserved quantity must be expanded to include the gravitational influence of the entire cosmos. The principle of energy conservation still holds, but it wears a new and more complex form, one where the energy of light and motion is in a continuous, silent dialogue with the energy of the expanding space itself. This cosmic perspective transforms a fundamental law from a rigid rule into a fluid, dynamic relationship. Perhaps the most humbling truth is that a star's great voyage has no final port. In an endless and ever-growing universe, the very idea of a destination begins to dissolve. Where, after all, could a star be traveling to when the entire map is stretching in all directions at once? Its journey is not a pilgrimage toward a fixed point in space, but a continuous redefinition of its relationships with everything else. The star is not moving toward a finish line. It is tracing a line that has no end. This path, the most fundamental trajectory any object can follow, is known as a geodesic. Imagine a world where the straightest line between 2 points is not always what it seems. On the curved surface of the Earth, an airplane's flight path appears as a gentle arc across our flat maps. In the same way, a star's path is the straightest possible route through a cosmos whose very fabric is curved and warped by the presence of matter and energy. It is simply following the natural contours of the universe, a path of least resistance through evolving spacetime. From the star's own perspective, there is no journey in the way we might imagine a ship sailing for a new land. There is only existence, a continuous unfolding along this cosmic streamline. Its life is not a trek toward a specific end, but a state of perpetual transformation. Its identity constantly reshaped by the stretching space around it and the shifting gravitational landscapes it passes through. This reframes the entire epic narrative. We are not watching travelers on a road to somewhere, but participants in an endless, evolving dance where the stage itself is growing, and the positions of every dancer are perpetually changing. The meaning is found not in the arrival, but in the motion itself. That faint starlight reaching your eye is a time traveler from a distant past. Each photon is a tiny capsule of information, a cosmic fossil preserving the exact conditions of its creation. When a star emits light, it imprints a unique signature onto those photons. This signature, revealed by a spectroscope, acts as a stellar fingerprint, detailing the star's chemical composition, its surface temperature, and even its immediate velocity relative to us. The light is a snapshot, a perfect record of the star's state at the moment it began its voyage across the void. But the journey itself then writes its own chapter onto this messenger. As the photon travels for millions or billions of years through the expanding fabric of space, its wavelength is systematically stretched. This cosmological redshift is not a flaw in the signal. It is a precise measurement of the total amount of cosmic expansion that has occurred during the photon's flight. The greater the redshift, the longer the light has been traveling, and the more the universe has stretched beneath its path. This single piece of data, the redshift, allows us to calculate the distance to the most remote objects in the cosmos, mapping the vast scale of the universe itself. Imagine a single photon as a tape recording. The initial recording captures the star's voice, its elemental composition and temperature. Then, during playback, the tape is slowly stretched, lowering the pitch of the sound. That lowered pitch is the redshift, telling us how long the tape has been playing. We can analyze both the original voice and the stretch to understand both the singer and the journey the song has taken. This is how we read the diary of a star's journey, using its ancient light to reconstruct a history we could never witness directly. The path of the light itself is also a record. A photon does not always travel in a perfectly straight line. When it passes near a massive object like a galaxy cluster, the fabric of spacetime is warped by gravity, bending the light's path like a lens. This phenomenon, gravitational lensing, creates distorted or multiple images of the same distant star. By studying these cosmic mirages, astronomers can map the distribution of both visible and dark matter in the lensing object, using the bent starlight to reveal the invisible architecture of the universe. The photon becomes a probe, its trajectory altered by every gravitational well it passes, its path a winding testimony to the distribution of mass along its route. So when you look up at the night sky, you are not just seeing points of light. You are reading a library of cosmic journeys, each twinkle a book telling the story of a star's life, its motion, and the expanding universe it has traveled through. The star itself may have died eons ago, collapsing into a white dwarf or exploding in a supernova, but its story continues, carried forever by its light across the growing darkness. From the fiery crucible of a stellar nursery to the silent expanse of the Degenerate era, a star's path is never its own. It is a narrative woven by invisible hands, a complex tapestry where the intimate pull of gravity tangles with the vast push of dark energy, all on a loom set by the universe's first moments. This is not a simple voyage with a final destination, but a dynamic and eternal state of becoming, a continuous redefinition of place and relationship across timescales that dwarf human history. The journey of a single star, in all its spiraling complexity, is a microcosm of the cosmos itself, its motion quietly shaping the grand architecture of everything. This perspective transforms the night sky from a static picture into a living, flowing river of light, where every twinkle tells a story of cosmic forces in delicate balance. If this voyage through space and time has sparked your curiosity, we invite you to join our ongoing exploration. Share your thoughts on these far future destinies in the comments, and subscribe to continue unraveling the profound mysteries of our universe together.